degraded circuit for which circuit to use. When you make IC chip, there are a variety of choices to use in terms of circuit technology. Well, you can use bipolar, TTL or Schottky, or bipolar ECL, or Cmos or Gallium Nitride. There are many choices. Usually the department of IC chip design divided into each circuit technology, and each department decide which one to use for making a certain function IC chip. And this was the tradition in the Silicon Valley. But I think the new way to approach this question, which circuit to use, is that there is a single planning department which look at all the circuit choices and decide what kind of function IC chip to be made by which circuit. Okay, so in order to do that, we have to understand advantage and disadvantage of each circuit. Now let's review quickly what the TTL look like. TTL is typical output voltage 3.4 and low is 0.2, so it's like 3-volt swing. Okay, so this 3-volt swing was okay before, but when the speed become concern, this voltage swing is pretty big, because what happened is all the circuit element transistors, it has a parasitic capacitor around, and you are charging, discharging every time when you switch the circuit. And 3-volt charging discharging time is pretty long. Okay, minimum 2.4 specification for the high, and maximum 0.4. You cannot be higher than this. And CMOS has pretty similar requirement, and the input has 2.0. That means there is a 400 millimeter noise margin, right? And here also 400 millivolt noise margin. So noise margin is about 400 millivolt, and that's a TTL circuit. And we're talking about outside of chip. Okay, ECL signal level is much more different. Okay, ECL, the circuit is it's inspired by the differential amplifier, and differential amplifier TTLs also came from the amplifier, right? So what happened is, this differential input, you have this kind of curve. So this side on and this side off, and you have a differential output. Okay, but ECL, the point is, this specification is so-called 100K series made by Fairchild. Motorola initially made a 10K series, which is very similar to this, but 10K is not temperature compensated. So you have this table for each temperature range. It's very difficult to use. Fairchild improved in a 100K series, so it's a temperature compensated, so it's across the temperature. Okay, but still the specification depend on VEE. Also ECL logic level measured from top to this voltage. Okay, so not like a TTL. TTL measured from ground to this. So typically what they do is, since noise margin is concerned, the stable ground is on the top, and they give negative 5 volt. And if it's a negative 4.5, negative 4.2 is slightly different signal. And again, this is the outside of chip. the ECL signal. And the ECL signal is usually it's come out and terminated into negative 2 volt. So you need a negative 5 and negative 2 volt for termination and stable ground. So ECL is something very difficult to use, but still it's used because you look at the high and low, it's only 600 millivolt. Okay, the TTL voltage swing is 3 volt. ECL is only 600 millivolt, very low swing, and this is one of big reason why ECL is fast switching logic. Okay, so for signal swing, TTL is large, ECL is very small, and TTL also has the transistor saturation problem, but that's solved by Schottky. You learned this in a previous video. The transistor is going to saturate. To avoid the saturation, you insert a Schottky diode here. Schottky diode, the cross voltage is low, so this point never go too low, getting into saturation. Okay, let's quickly review what the saturation is. Transistor saturate, okay, when you apply, this is wrong, CE voltage, when it's on, what's happened is this P type, the positive voltage inject a lot of hole, and negative side inject a lot of electron, and recombination happen here. Okay, so what's happened is electrons are attracted to be range, but instead of recombine with the current provided by IB, it swiftly go up here. So the current flow this way, and that's what transistor is. This base emitter is forward voltage, so recombination happen. This recombination, electrons are injected into P area, but instead of recombining, majority goes to the N type on the collector. So you have IC, and this voltage is EC, BCE. Okay, the transistor show this kind of characteristic. For given base current, when you increase VCE, it's kind of stable IE. So the IE is a function of IB, right? Okay, so transistor, this is VCE, is logic low. This is high. So what's happened is, when you operate in this range, it's no more transistor on and off. But if you let it flow too much current, this voltage goes down and get into saturation mode. Okay, once transistor goes saturation, then it's choke off the current. So when you this is input is low and transistor voltage goes high, output is high, input is high, the base, okay, and when input is high, VCE, this drop down to very low, okay, then saturation recovery is going to be very slow because you have a capacitor here, and this is not the correct representation of capacitor. Capacitor is inside collector. And in order to bring this voltage up, you have to provide a charge to the capacitor to bring this node up, voltage up. But you're choking off the current because of saturation, so it takes a long time. So after transistor turn on, this turn off after turn off, the recovery to high state is going to take a long time, and this is the slow switching. Okay, so the Schottky, once the Schottky is inserted, then it's operated around here. Schottky voltage is in this region, and it's clamp VCE at this point, so it's never go saturation. This range is never go there. Okay, so this is a Schottky TTL, and low power Schottky means even reduce the power is still fast, so it's called low power Schottky. Now TTL has this Schottky diode utilized for input. This is input, and this is the output. This is like IC chip. Low power Schottky input stage is like this, and output stage, and it's called the tri-state output. That means output can be high or low or high impedance. So high impedance state. Okay, why high impedance? High impedance is used for bus connection, when you connect this output together with other chip, and if this is high impedance, this output determine high or low. Okay, so the best strategy is to use inside a chip. Inside is ECL, because ECL is a differential amplifier style. It's never go saturation, and you don't need a Schottky. So you have a TTL input converted to ECL circuit, which is much faster and more efficient, then converted to TTL again to go out the chip. And this is the best strategy to use. The output is, the input is so easy, right, to convert it. The once you get in, this can be driving ECL circuit. Okay, so it's straightforward. Converting ECL to TTL, you put something like something that instead of this and drive this guy, then it's converted to the TTL. So in this case, it's same VCC. So inside you need only VCC, which is 5 volt, and the ground, and it's look like a TTL chip. And the ECL you can integrate pretty well, because a lot of SR latch and flip-flop, ECL is much more efficient than TTL, and in terms of number of transistor and power. So this seems to be the way to go. How about CMOS? The CMOS, you have a CMOS operation is very different, because when this is high, then you have a parasitic capacitor you have to charge up to bring this node up. So the current flow here, okay, and when it goes low, this current is discharged because this is going to be on. So CMOS, the current profile is like high to low transition, the current flow, and once it's low or high, there's no current, so it's very low power. That means it's good for large integration. Okay, so CMOS, like a CPU CMOS chip, what's happened is it's consume a lot of power when clock speed is high and many gates are switching. Okay, when it's not doing anything, then power goes low. So the total power going to CMOS chip depend on what chip is doing. Okay, but it's average out because usually it's large concentration. So the large LSI or VLSI, very large chip, the CMOS is the way to go to mostly reduce power. And speed is low before, but nowadays they're using 7 nanometers, very tiny gate. So this capacitor is so small, so the speed went up. And even they have gallium nitride. What gallium nitride is about is it's a turn on resistance is low, so this RC constant is much small. It discharge very quick and charge up very quick. So this increase the speed a lot. Gallium nitride. Also, the parasitic capacitor is a little bit low. So gallium nitride is for high speed. But the problem is this is costly. It's not for large integration, because what they do is you use a silicon substrate, and you have a silicon, you put the layer of gallium nitride, and this prone to defect. So if you make a large circuit, you are suffered in yield. That means you don't get many working chip. Why you use a silicon substrate? Because otherwise it cannot use existing fab. Fab is the production facility for silicon chip, and this all adjusted for silicon wafer. And silicon wafer, like scribe and break it, all the machine tool is adjusted of silicon, not for gallium nitride. So what you do is basic substrate, you make a layer of gallium nitride and try to use gallium nitride. It's an improvement in the speed, but higher cost and low integration. So the application is limited. The CMOS circuit is the way to go for the large integrated chip like a CPU and other complicated function, AI CPU. But when it's come to small to medium, high speed, definitely the best way is to make a TTL compatible, which is CMOS compatible, but the inside all made with the ECL, high speed. So that's a kind of the current circuit technology adapted in the most of cases. Okay, so if you like this video, please move on to the next one.